Good morning, Emmanuel. Good morning, everyone. I am Georgette Sow, the Director of Communication at AI4PEP, Senegal. I am thrilled to be moderating this first lecture on AI for Dummies. I'm so happy to introduce our first guest, Dr. Emna Harigua, an assistant professor bioinformatics and artificial intelligence data science at the Institut Pasteur de Tunis in Tunisia. Dr. Emna Harigua is a bioinformatician, as I said earlier, and a data scientist with a multidisciplinary profile. She holds an engineering degree in analytical chemistry and a master's degree in information processing. She did her PhD in structural bioinformatics applied to drug discovery at Institut Pasteur in Paris, France. She has occupied a postdoctoral position since 2016 at Institut Pasteur de Tunis, where she was focusing on developing cutting-edge approaches in structural bioinformatics applied to infectious disease. Her research was further focused in 2019 to the development of artificial intelligence for health applications. She's currently an assistant professor at Institut Pasteur de Tunis, like I said earlier, leading a team developing bioinformatics and artificial intelligence-based approaches for biomedical research applications. Dr. Harigua leveraged multiple grants with USAID to support her research. The latest is the highly competitive ARISE grant from the AIS towards implementing an AI-based platform for drug discovery. She has been a reviewer for multiple grant calls from the BMGF focused on AI deployment in the health sector and was a member of the scientific committee piloting the report by the BGC and Wellcome Trust around the potential of AI in the drug discovery field. Dr. Harigua is a recipient of multiple awards and distinctions, including the International Fellowship of UNESCO L'Oréal for Women in Science in 2012, the ASTMH Society Fellowship, the Ersin and CalMet Fellowships for Doctoral Studies. She is the founder of AI4PEP, a startup development digital tools that brings the AI usefulness to health workers and clinicians. Dr. Emna, I welcome you.
Thank you very much. Thank you for the introduction. I'm very pleased to be here and to be the first lecturer on this lecture series, and I really appreciate this initiative from your side. Thank you very much for the invitation.
So, Anna, if you can go ahead.
Khulud, go ahead.
Okay.
Introduce
Okay, hello everyone.
Sorry.
Welcome to today's webinar. My name is Khulud Boltan. I'm thrilled to be one of your moderators for this session. I'm currently a doctoral student in analytical chemistry at the Manar University in Tunisia. So together we are thrilled to guide you through today's session, which will explore artificial intelligence for beginners, dummies. We have an exciting agenda lined up with our esteemed speaker, Dr. Emna Harigua. I believe that her expertise will provide valuable perspective and spark stimulating discussion. Following the presentation, we will open the floor for the question and answer session. This is your opportunity to ask a question and engage together directly. And after that, we will wrap up with some closing remarks, summarizing the key points discussed today. So please feel free to submit your question through the QA panel. And if you encounter any technical difficulties, please use the chat feature to notify our support team. And Dr. Emna, the floor is yours.
Thank you very much. So I tried to get my slides on.
Okay.
Can you please give me the hand for that?
Dr. Emna, it's a green button at the bottom of your
Yes.
screen.
It says I am not allowed as a participant to share my screen.
Yes, please
So I
allow
need your
her
permission.
as a host or co-host, Emmanuel.
So in the meanwhile, let me start by very quickly introduce what I do. So thank you for the introduction. I think you presented me in length. So I'm Emna Harigua, and my field of expertise is bioinformatics and artificial intelligence applied to drug discovery, but not only. So today I'll be trying to kind of introduce what is artificial intelligence for novices. So by using the word dummy, I think that we can all be able to understand what is it, and I'll be trying to have these very basic concepts of AI that would help our students today to be able to understand what is it in concept, but also be able to understand in which cases they are able to leverage or use AI. So indeed, now AI is basically everywhere in our life, especially if we are users of technologies. So there are some applications that are obviously based on AI, like application on the phones that can retouch photos, the use of ChatGPT, for example, when we are asking questions and getting information. But there are also a lot of tools that are hidden and that we are not aware of. So artificial intelligence is really everywhere and invading all aspects of our lives. So I went and asked our great friend ChatGPT, what is its definition of AI? Should be accurate, and it is. So it defines AI as computer systems and machines that would be able to perform tasks that typically require human intelligence. These include understanding natural language, solving problems, and making decisions. And then it adds that AI systems would use algorithms and data. And I'm really highlighting this. So it's not just about the algorithms, it's also about the data. And this system would use algorithms and data in order to learn and improve, in order to adapt for new situations. So this is the force and the importance of AI. So artificial intelligence is now very popular, but it has been there for now multiple decades. It's not a really new field, but it's now getting very, very sophisticated, mainly because of the power of the computers that we have, but also the amount of data that exists today in our world, digital data. So artificial intelligence is a very wide field that denotes any type of program that can sense, reason, act, and adapt. And then we have inside it the subfield of machine learning. And today we will be focusing on machine learning and its subfield called deep learning per se, in order to kind of understand what are the basics of these applications and these algorithms. The difference between machine learning and classical programming is the fact that in classical programming, as you see in this figure, would take rules that are hard-coded by the programmers and then data. And for these data, they will be providing answers using the rules that have already been coded. Machine learning acts differently. So it takes data and answers related to that data. We call these labels in machine learning. And then it will draw its own rules and then be able to give new answers for new situations. So we are not hard coding the rules. The idea is that the algorithm itself would try and address its own rule based on the data. So depending on what data, what answer, the rules will be good or bad. And this is why data is very important in the machine learning pipeline. So a more sophisticated or scientific definition of AI or machine learning is that a machine learning algorithm would be a program that is able to learn from an experience E. So these are the data. With respect to some task T, these are the labels, what we called answers, and have some performance measure, which is P. So if the performance on task T measured by P would be improving with the experience E, which is the amount and quality of data that we have, then we will say that our algorithm is learning. So we only talk about learning when we have a measurement of the performance. So this is how it works. If we use the subcategory of classification, and we will be talking more about the classification concept. So what we have is that we have a training phase and a prediction phase or testing phase afterwards. First, in the training phase, we'll be having the data plus their labels, and we call that labeled data. And then we come up with a machine learning algorithm that can read this type of data and learn. Then we come with unlabeled data. So these are data we don't know the answer. And we feed these to the model that have already learned. And we expect this model to come with predictions and answers. We have different categories. We have the supervised machine learning algorithms. And in this case, what we do is that this is what I have been explaining. We come up with labeled data set, and we expect the algorithm either to classify, so we call this classification, class A, B, C, or to perform regression, which is predicting a continuous outcome. So this is fitting experimental data points into some sort of function. It's called regression. So the difference here is that for one case, the labels are discrete values, class A, B, C, and for the other one, it's a continuous function of values. Then we have what we call unsupervised machine learning, and the idea behind is to discover patterns and create new clusters within the data. So we don't know any classes, and we don't come with labels. So clustering is mainly learning features on the data and trying to discriminate these data points into different clustering. So that's the difference between classification and clustering in machine learning. So let's get back to the classification case, and we will be trying to understand how it works. So basically, we come with different data points. So here we have the different images that are classified into different categories of fruits here. Out of this data, we will have to extract features. These are called features or descriptors. And these are information that are encoded into numerical vectors most of the time. And that's what the user or the machine learning engineer will consider as a very good way of describing the data in order that the algorithm would be able to discriminate the different classes. So we extract features, we train the models, and then we have a model that had learned. Then we test how the model is doing by feeding it new data with no labels, extract the exact same features, and use the learned model to return some predictions. So the feature extraction is have been a very human extensive work within the machine learning algorithm or pipeline. And the idea is to identify an optimal set of descriptors that would make the AI algorithm really able to discriminate classes and objects. So most of the time, this is where we bring people from a field of expertise that have a big knowledge of the data that we are treating. So it depends on the data, and this is what we call field expertise. And the people are their work is really to identify what is the best way of describing the data so that the algorithms will be able to learn. So up to now, we are not doing really the machine learning per se, but this is very important. What are the data and how do we describe our data in order to be able to apply the machine learning algorithm? So we have some rule of thumbs to this part of the pipeline that is called feature engineering and selection, where we try to have many independent features that do not correlate with each other in order to be able to make the learning easy. So it's basically what makes the machine learning algorithms very capable with high performances, even if the machine learning algorithm that we'll be using is a very basic one, can be logistic regression or any type of simple state-of-the-art algorithms. But once the features are good, most of the time we will be able to learn. This is very important. And we are talking about this because this is what made the deep learning algorithm a real breakthrough in the field. So deep learning algorithms are a subset of machine learning fields that are focused on neural networks. So neural networks can also be used in the frame of what we call machine learning. And we will be having our input, we will do our feature extraction, and then we will be having a multi-layer perceptron, which is an artificial neural network that will have similar layers, and it is able to do classification on whatever.
Emna, we are not hearing you anymore. Can you speak to your microphone, please?
Dr. Emna, we cannot hear you anymore.
Can you hear me now?
Yes.
Yes, we can hear you.
Okay.
Do you mind going back to the previous slide because we could not hear you? Thank you.
This one? This
Yes,
one?
please. No, the one after this one.
Okay, so the deep learning. Okay.
Deep learning. Yes, thank you.
Yeah, good. So as I said, we have what we call the neural networks that have historically used, still used in the machine learning pipeline as classification algorithm. They are very powerful and can be used after feature extraction steps, like in any classical machine learning pipeline. Now, what deep learning approaches have brought to the field is that we will be using very deep neural networks, and this comes into multiple layers. We will talk about the layer thing in a few minutes. And in this case, we will be having an input that will be automatically feeding or like systematically feeding without doing any feature extraction. And we will rely on a series of neural layers that you can see here as columns of rounded shape neurons. And we will rely on these layers to extract the features for us. So what it brought to the field is that instead of biasing feature extraction based on what we know as humans, we will let the data state what should be extracted to this neural network. And for this case, we need very deep neural network, we need a high performance computers, and we need huge amounts of data. So artificial neural network, just to explain what is it, it's a mimic to the human brain functioning. So it is a simplified and a representation, but still it is mimicking how the neurons, biological neurons would work. And the idea is that we will have some input coming that then will be fed to this series of layers of neurons, artificial neurons, will communicate between each others and then feed in a final information to the latest layer called F here in order to return an information or a decision. So it basically comes into this shape, but here instead of having layer 1 and layer 2, we will be having sometimes 50 to 70 hidden layers depending on how big the architecture. We will be having the input, we will be having different types of layers that are able to extract features, and then we will be having at the latest part of the neural network the classification layer, which is here, this one. So I am not going to dive into the mathematics. Of course, this is an initiation to artificial neural network, but it's basically comes down into mathematics in order to understand how information is transmitted from the input layer to one of the hidden layers here, and how the different hidden layers will be communicating information and taking decision what is to retrieve as information and what is to be discarded as noise. So here is an illustration on how some highly connected convolution network would work. So these convolutional networks are very sophisticated architectures that are very successful in extracting information from images. So here, as we see, we are trying to do some facial recognition. And when we go, so we feed each of the images into the input layer, the first one here, as a simple vector of the image. And then we will let the different layers, here we have only 3, but is much larger than that. And the idea is that the first layers will be extracting very simple features, as you see here, just edges and forms. Then as we go deeper in the neural network, we will be differentiating pure features of a human face. And then at the latest part of these convoluted neural network, we will be having real faces that appear. And then we will be using a classification to decide who is that person, depending on what type of information we have. So CNN, convolutional neural network, are very popular in order to mainly analyze images and videos. We have also what we call graph convolutional network, and these are neural networks that convolute graphs and are mainly used to identify information that are encoded into networks. These can apply to social media information or to protein-protein interactions in biology, and so on and so forth. We also have a recursive neural network called RNN, and these are basically the most popular algorithms behind natural language processing. We have different types of them, and we can cite the latest in generative artificial neural network that are called the transformers, for example. So this is basically the basics to what is artificial neural network and how it works. Now I'll be trying to illustrate real cases and research work that is done in the biomedical field, really to bring closer to you to which extent AI is of use and how diverse the application can be, even in one type of subfield, which is the biomedical field. So here I'm giving you examples of some success stories, successful use of AI in different subfields of biomedical research. So we have now Benevolent AI. It's a company that is now worth $2 billion that is working using AI for drug discovery. Then we have the very known AlphaFold that have been released recently by DeepMind in collaboration with EMBL EBI. And it's applied to structural bioinformatics, and it's basically for protein structure predictions. And then we have multiple applications in analyzing biomedical images in order to do diagnostics or to understand some pathologies using medical images. Now I'll be giving you examples of what I have been doing in different type of projects related to these subfields of the biomedical field. So the first one will be project one. It is about image processing, and it has been developed as part of the startup AI artificial intelligence that I founded into 2020. So the idea behind AI4HD is to develop e-health solutions for decision-making tools that would help clinicians enhance patient management, either through diagnosis or triage of cases based on artificial intelligence. So the idea is to develop a mobile app that through a simple photograph of a lesion, cutaneous lesion of the skin, we will be able to use our artificial intelligence tool to predict whether it is cancer or whether it is cutaneous leishmaniasis. So now the number of clinical cases and diseases that we are focused on is restrained because we need more data on different pathologies in order to have it applied to other skin conditions. So in order to do that, we first started by optimizing our artificial intelligence pipeline. We started by collecting data. So data is always very important. I am not to be very long about this. We have scrapped data from the internet, used open sources information, and then we used different types of artificial intelligence tools. The first one is YOLO, which is you only look once, and it's a tool for region of interest detection. So what it does, it detects the lesion out of images that look like this. And the idea is really to finally identify images that contain only the lesion, that then we went through the segmentations through different type of algorithms. So here we use VGG16 to do this, and then finally we performed disease classification using different types of convolutional neural network. We have 3 models that performed very good predictions in terms of accuracy, and then we have model 2 that we are trying to enhance and to validate on clinical images issued from our partners in CSU Rabta, namely Professor Mukni. So that was the first illustration on how we can leverage AI in order to enhance the clinical triage and diagnosis of a patient with cutaneous condition. The second one is a project that is based on structural bioinformatics. So for the first one, we were using images. That's the most, let's say, straightforward use of convolutional neural network. And now we will be talking on how we can use machine learning algorithms. This is now unsupervised learning using self-organizing maps in order to identify the best site for docking over protein structures. So proteins are 3D entities. These are biological molecules, and they have a given shape and a given form. And then we try, and they will be contained in some cavities. And the idea is to try and identify which are the cavities. Also, we call these binding sites that will be the best suited in order to dock on some inhibitors for drug discovery. So that's the main, the final goal. So our work is basically to do a docking of multiple molecules and then use that information to identify preferential positions on the 3D space of all the molecules that have been docked. So here we have multiple hundreds of thousands of molecules that are docked on each protein. So what it does is that the 3D self-organizer maps that we implemented will be shrinking the space. So it basically goes into a sort of a cube of neurons that are randomly spaced in the 3D space. And then they will be learning over the decomposition of the molecules that we had and shrinking and gathering into what we call populated clusters. So this is clustering here. And then you see here over the space, so these are 3D maps that will be shaping and shrinking based on what are the preferential position for all atoms on this protein. And the idea is to identify these very populated clusters as potential binding sites. So our methods have been very able to do or compete with state-of-the-art algorithms back in the day, and also to be better than some of state-of-the-art algorithms when compared to that through a benchmarking. Now we will move to the third illustration and drug discovery. So as you see, each project will be using different type of data. And for the third one, it is also a new type of data that we will be using. So drug discovery, here I'm talking about the funds and the projects that I have been conducted. So we have been working on this since 2017, but we leveraged funds started in 2019. And now we have funds that will combine us into 2027, where we are trying to leverage AI and bioinformatics both in order to have a platform for drug discovery against infectious diseases and other type of diseases. And the idea is really to develop the AI, but also to discover new molecules. So drug discovery is a huge pipeline that would last up to 15 years and cost a lot of money in order to get one molecule approved and become.
We're losing the sound again. Emna, can you put the microphone close to? We can't hear you. Thank you.
Is it better now?
Yes, it is better now. Thank you.
Okay. So drug discovery, as I said, is a very long process and very costly. And when we try to understand what is happening, so I'm not be very long on these slides. These are coming out from the report by BCG and Wellcome Trust, in which I have been part as part of the expert panel to deliver this report on the landscape of AI and drug discovery. What we see is that, for example, so we are operating into the small molecule subfield of drug discovery. And what we see is that the use and adoption in low to middle income countries is 50% of known when they have performed questionnaires for scientists based in low to middle income countries. We have little and very low rates of adoption of AI into the pipeline, which is different in high income countries. Then we have been performing pain points analysis. So what is the problem, and trying to identify how we can really work on this. So we saw that the lengthy cycle for discovering and optimizing molecules is a problem. We have an issue with data and exploration of chemical space. And we have also lack of ADMET data for optimization steps. And then we assessed what is the impact of AI into the drug discovery. And we saw that we have high impact, mostly into the hit to lead and lead optimization steps, and that there is a lot of effort done into the repurposing and identification of novel molecules. So this is what we do in our group. And if we come back to the pipeline of AI, we split it into the different steps, and it's always started with data set building and curation. So we need to have good data that we will be reprocessing and encoding. Then we will be using the machine learning and deep learning models that we train and optimize, evaluate, and then wherever we have a good algorithm, we will be able to deploy it for use. That's how we work. This is why we will be delivering in our buying platform different things. So we have first the database, then we have the AI frameworks and algorithms, and then we will have the outcomes of the AI, which are novel molecules to be validated experimentally. So let's start with the data. We first implemented CDOS-DB. It's a database and a web platform where we have been screening the web and different databases like PubChem and other in order to collate very interesting data sets. We started with leishmaniasis and coronaviruses, and we are extending this to different diseases. And what we saw that we have a lot of information that is issued from the literature, which means in publications. So these are data that is not structured and can be very difficult to use in AI. So what we did is that we extracted these data and put it into CDOS-DB for both diseases, leishmaniasis and coronaviruses. We ended up with more than 100,000 of data points in our data sets. Then we worked on these data sets and we extracted the most significant part of it, and it comes to up to 4,000 molecules per disease. That can be searchable very easily using our database. So it is, I forget to put the link, but I can send this. So it's available online, can be used by anyone, and the publication is submitted. And we can use directly the prediction function here. So we have the search function and the prediction function where you can use pre-implemented machine learning and deep learning algorithm to predict activity of the molecules. So it's a seamless access to machine learning and deep learning. Oh, here is the link. It's CDOS-DB at Streamlit.app, and I can send it later if anyone is interested. So once we have CDOS-DB, this database and platform, we started developing the machine learning algorithm. So we used what we call the central information in CDOS-DB, which is the structure of the molecules. That's basically what we use. And then we work on encoding this data. So the encoding is the feature extraction part. So it's either done through molecular fingerprints or graph convolutional network when we are using deep neural network. So the first part of the neural network is a convolution layer on the graphs, as we see chemical molecules as undirected graphs. What we do is that collect the data, we encode them, depending on whether we are using deep learning or machine learning algorithm, we do the training and then the prediction. We are also working on generative AI, but I won't be talking about this today. Basically, we use all the data that we have. I'm skipping these slides. And using the data encoded in using different tools, we have been training 7 machine learning and 4 deep learning algorithms. And we saw that SVM or random forest among the machine learning were the highest performances. But our interest here is to identify what are the deep learning algorithms that can achieve as good performances as machine learning. And then we identify GCN and DAG as one of the good performances among the deep learning algorithms. We did very high optimization, multiple optimization of these architectures. We validated that they are doing well in using different metrics. So we do not only look at accuracy, for example, we also look at ROCA-UC, recall, Cohen kappa, F1 score, and MCC. And we also make sure that they are doing good different levels. Why? Because it's very important to identify algorithms that are able to distinguish the classes, but also that will have low percentages of false negatives and false positives as well. So then when we optimize our models, we performed what we do an assessment of their generalization power. So generalization power is basically the capability of an algorithm to render as good performances as what you see during the training and evaluation when it is assessed on never seen data before. And what we saw is that even that machine learning have been the best performances up to now, the neural network, the deep neural network, GCN mainly, was the best model to be able to generalize from category to category or to new unseen data. We have performed external validation. So this work has been published. I'll be trying to go very fast for the sake of time. But here I'm just illustrating that we were able to have at 80% confidence predictions that come 5 out of 8 approved drugs that are really active. So this is a very high performance. This is more than 50% rate of success for our algorithms. So we have also applied approaches. Here I am showing the work. It's a similar pipeline using machine learning algorithm, but this time on leishmaniasis, not COVID-19. And out of the work that we have been doing, we have work that will be published. We have Masmoudian all in preparation and Walha was submitted. So the work by Dr. Walha is basically about novel molecules. We have 9 anti-leishmania molecules that have been validated in the lab. Out of them, 3 are very promising drug candidates that we would like to pursue for further validation. So a take-home message from the lecture of today is that data is as important as the algorithms. Whenever we are doing machine learning, it's important that we bring experts of the data into the pipeline. It is not only about having AI engineer or scientists specialize in the machine learning and deep learning. It is very important to specialize also in the data in order to optimize the work. And then we have very promising work with graph convolution approaches in the drug discovery. So with that, I would like to thank you for listening, and I would like to acknowledge different members and colleagues that have been involved in the different projects that I have been showing today. And I'll be happy to take your questions.
Thank you, Dr.
Thank you so
Emna.
much.
Thank you for this relevant presentation. We will now proceed the question and answer section of our webinar. We have already 61 participants, so we want this to be an interactive session. It's a great opportunity to share ideas, so please seize this opportunity with Dr. Emna. Okay. Don't hesitate to take this chance and ask a question.
I'm going to go ahead and read the 2 questions that we have in the chat. So, Dr. Emna, we have someone asking, how do we know how many hidden layers to choose when performing convolutional neural network? I cannot hear you. I don't think anyone can hear you, actually.
You hear me now?
Looks like yes.
Okay, sorry.
So that's the first
myself.
question. I'll let you answer that one, and then I'll go ahead and read.
Okay, so
Thank you.
This is a very relevant question, actually. We have a rule of thumb, so it's not a number of layers. It's what we call a certain depth to the neural network that is, of course, dependent on the number of hidden layers to be chosen. So if the data is very complex, and then you have a lot of data, you can have a very deep neural network. So it is good to look at the literature and see what it comes. and what people are using in terms of size of or number of hidden layers. Then if you have a simple task of classification and you're not doing very complex tasks, it is better not to have a very deep neural network because it's going to learn more than it should. And then we will be talking about either overfitting or problems of lack of convergence. So the algorithm does not converge and is not able to do the classification. So it's very important that you see what the teacher is doing, and also and that's apply in any type of AI project that you would like to do. Benchmarking at the start, different different depths of the network is very important.
Thank you, Dr. Emna, for your response. I'll go ahead and read the second question from Jilan. Is the choice of supervised and unsupervised learning depends on our raw data and more of them? We cannot hear you, sorry.
Can you hear me now?
Yeah.
Yes.
So if you don't have labels to your data, you can do supervised machine learning. So it depends on the data. Now, sometimes we would be having labels, and maybe we are trying to see if there are any subcategories. So we do unsupervised learning. So we put the labels aside, and we do unsupervised learning and look if there are any subclasses or new classes or there is any class that can be divided into the data. But it's basically what we have as data and also an objective. So if we have labels and we are trying to classify, it's basically supervised. And when we have data and then we are trying to understand what differentiates these data from each other, and get them into different classes that have no predefined labels. That's unsupervised learning. That's the difference.
Thank you, Dr.
Thank you.
Emna.
Yeah, just a reminder that participants are more than welcome to send their questions on the chat, or just basically to make it more interactive, come in and ask the questions. Thank you.
Okay, so another question, how we could be part of the change, from Carla.
Well, now we are in a very, very intriguing and very special phase and era where we have all these type of technologies that are almost can be used by anyone. So now it is really, so your series is called Decolonizing AI. And the idea is also when we have frameworks and open source initiative on AI, the idea is also to democratize AI, which means that even non-coding people can use it. And this is why we have developed CDLTV. So we work with many people and we see in the field that there is a lot of people that have a lot of expertise and can have very nice scientific questions to ask, but these people do not have the skills to implement AI. And the idea is not to get everyone to become an AI engineer or an AI expert doing the coding part. Mm-hmm. The idea is to see how people, so this is why we need people to understand what is AI. You need to understand the pipeline, what should be prepared upstream, downstream, the machine learning algorithm, and downstream it. So this, the both parts of the pipeline, in order to make sure that anyone with any expertise on the data and the field, even with no very no big expertise in the coding can also use AI and leverage it and have advances in the field. So there are a lot of initiatives like ours in different fields. So this is drug discovery, but probably there are other initiatives. And the idea is that it is good to have this AI literacy initiative make people understand how they can use AI if they are not interested in being AI experts. And it's even if you're a good and expert user of AI, you can make a lot of change. Now it's becoming really very easy, and it's very important also to be very critical and not choose any type of tools that are out there. We need to be critical and choose on the tools and make sure that we can do really benchmarking of performances and be able to use the accurate ones, because there will be a lot of them out there.
Yes, I'm totally agree with you, Doctor. And let's see the other question. So, what tools should the biologist use, master, in order to be able to use AI and apply it to its data? Which bring another question: how dependent a biologist can be to informatician while applying AI?
So yeah, it's basically what what we have been saying, but I'll try and add more on that. So the tools, there are many of them. So when you're using a tool, it's very important to go and read what type of research publication are behind. So you want to make sure that the people that are deploying tools are experts in that field, and that they have all type of evaluation and validation of their tools from the informatics and algorithmic parts. Then you will be using that and be very critical about what it rendered. So in order to be a very efficient user of the technology, this applies to AI, but also applies to any type of computational tools that are out there for bioinformatics and computational biology. You really need to understand how things work. Not necessarily be able to implement the tool yourself, but you need to understand what are the pitfalls and what are the drawbacks of any type of technology. So AI, like any type of computational or predictive tool, it's a predictive. When we talk about prediction or model, we always talk about error in there. So it's never 100% correct. So you need to take into account that. And this is why I'm saying you can become an expert user and understand what type of AI should be used. It's a lot of search and literature. And to respond to the second question, it's not about being dependent on informatician. It's best to have a good collaborator that will avoid you doing or using bad tools or interpreting in a very erroneous manner what an AI tool is giving you. So it's not a dependency, it's rather should be maybe a type of a collaboration that will help you really use correctly the tools if you don't have the expertise in assessing what type of AI is to be used. But now there are a lot of tools that are published, they can be used. Just be careful and have a critical eye on that.
Okay, thank you again, Doctor. And Mr. Sadri Znaidi, go ahead, please.
Hi, Emna, do you hear me? Hi, everyone.
Hi, Sadri, how are you?
I'm doing great, thank you. What a great talk. Thanks for sharing it with us. I have a question pertaining to the drug discovery part that you explained at the end of your talk. Amazing, the list of small compounds and chemicals that you could propose for anti-leishmania disease and infectious diseases. My question is, based on your analysis, and at the end you have this list of database of molecules that are could potentially be used as anti-infective. Is it possible also, or should one think that the way those chemicals are prioritized or delivered as an output, could one also be able to extract some additional information, especially information that could potentially suggest the mode of action in the pathogen itself as well?
So thank you for the question. As if we come back to the very beginning of the presentation, I have defined the AI as having an experience, learning over a task, and then enhancing a performance measure. So the task here, which is the mean or the way that the compound is acting inside the pathogen, is not necessarily what we have in our data set. So in order to have that type of information, you need your data to contain that type of information. So depending on what you're trying to do, whether to identify whether the molecule is active or not, or to assess an IC50 value, for example, against a given pathogen, that's one thing. The other thing, if you're trying really to understand what type of mode of action and what type of pathways are maybe hindered by that molecule, you need to have that type of information in your data. So for now, we don't have that much information on the pathways in our data set. For the Leishmania data set, we have, I think, 30 to 35% of the molecules to which we have that type of information, which means the molecular target or the pathways, things like that. But it's not there for all the molecules. So if we would like to go further, we need to have the specific data set that will give us that information. And then we will be able to do the work from the AI part. So see how data is really what determines what you do exactly with your machine learning or deep learning algorithms. But this is very feasible, given that the data is there.
Okay, thank you so much.
Looks like we have another question in the chat from Haifer. Hello, Dr. Emna. Thank you for the clear and interesting presentation. I would like to know the future of AI in healthcare, particularly in cancer treatment. Thank you.
Okay, so cancer, so I have been presenting work that is about infectious diseases. So cancer is also a disease, but is a multifactorial disease. And cancer should be, at the same time, one of the easiest disease to work on, and one of the most difficult disease to work on for two reasons. So first, we have a lot of data on cancer. That's one of the most studied diseases, and for which we can identify data sets that are of use for machine learning and deep learning. And most of the first chemoinformatics, then came the machine learning analysis projects, started with cancer indeed, and not infectious diseases. Now, where cancer is complex, cancer is not about having a pathogen doing something to the disease, although I know that each biological system is quite complex. It's not as easy as just killing a pathogen and getting rid of the disease, of course. But cancer is one of the most complex diseases that are out there. And I think that there were probably a lot of work that is trying to really leverage one of the most complex type of architectures and deep neural network to study cancer. So our group is also interested in cancer treatment. We have been starting this work. We are not yet talking about the results, but we are trying not to tackle it in a very naive way, where we will be just using active, inactive molecules. We are trying really to have experts with us that will help us dive into the complexity of the disease. And so we can have simplistic approaches to cancer and get out of it with new molecules. This can happen. But from our side, we are trying really to look at cancer in its whole complexity and try to see if we can include any type of environmental or genomics information in there before deploying any type of pipeline.
Okay, thank you. So please provide your feedback on the link in the chat. And let's see another question.
There is Mustafa Fai.
Okay. Mustafa?
So, thank you very much. Thank you very much. I'm very happy to join you today. I come from Senegal. I live in Quebec City 15 years ago, and I do research on medical anthropology of medicine. I focus on sexual reproductive health, vaccination, immunization in West Africa and Senegal about HPV vaccine. And now I listened to this presentation, this kind presentation this morning, but I have some some question about IE and response and pandemic. You know, because today IE is and mod and a phenomenon, a new phenomenon. I think it is a phenomenon, and people people around the world in academia area, they talk every day. I you know, because I think about pandemic issue, I can be used very efficiently. But my question is, what do you think about IE and pandemic West Africa country? Yes. What do you think about IE and pandemic situation issue in West African country? Thank you.
Thank you for this question. When it comes to pandemic preparedness or like being able either to prevent new outbreaks or being able to monitor health situation in terms of maybe in times of pandemic or epidemics in different parts of the world. This type of application is very, very dependent on digitizing the health system. So if we don't have enough data that is out there, it's ready for use by the AI algorithms, it is very difficult to implement highly sophisticated approaches for pandemic preparedness or optimization of the healthcare system. We saw with COVID-19 a sort of explosion of startups, innovative projects. Some of them were very highly successful in order to help with these type of questions and how. But what we saw also that in countries where the health system or any type of information system is not digitized, it is probably the most the biggest issue to leverage in AI. So if you don't have accurate data, if you don't have enough data, if you don't have data that represents all type of categories in your society or in the patients that you're targeting or the type of hospitals you're trying to help, etc., it is very difficult to have good results. So before talking about AI in this case, it is very important for any country to work on digitizing the health system and to have really data collection and curation systems that is designed for the future and for the present, so that we can very easily use the AI. So the AI is not of a problem. If the data is good, it is there.
Okay. Thank you. So another question about the future of AI. In doing literature review, can you suggest any of the algorithms that can help?
So yeah, so AI for literature review have been there for a while now. It's there have been multiple algorithms. So depending on what you're trying to do, whether having an algorithm that will help you target the best papers to be read, or whether you're trying to extract information from papers without reading a lot of papers. So that's called automatic data retrieving from the literature. So for the first part, if you're trying to target reviews, I can't recall the name, but there is a new application that appeared. It is like ChatGPT. So it's the same concept, but it applies to academic papers. So it will come back with information telling you that, let's say you're asking, can I have, what are the molecules that are used to treat COVID-19, for example? Or how many new molecules have been now validated and into the clinical trial for COVID-19? And it's not going to return information issued from internet. It will be coming with information retrieved from scholarly databases and scientific literature. I can't recall the name. I think one of my colleagues is probably in here and can drop it in the chat. And so, so it's great because it can help you get easier into the information and shorten the time of literature review. But it is very important to verify all type of information. So for academics, for scientists, it is not acceptable just to get information out of these type of AI applications and put them into a dissertation. So I'm not encouraging that type of use. I'm saying it is good to use AI, but you need to be the master of our work.
Yeah.
So that's for the first one. The second one, there are multiple also algorithms. These are recursive neural network based approaches. And these are algorithms that have been used for large databases also in order to extract information from the literature about, for example, new validated genes correlated with type of pathogens, and they are feeding multiple databases, and then people that are looking after the databases need to do some data curation afterwards. And then I know that there are a lot of type of algorithms that are used to extract biological activity of chemical compounds that are there in the literature. And we have been using these type of algorithms to feed TDOS-DB at some point. So yes, the literature is very rich and there are a lot of algorithms. So yeah.
Okay, thank you. So how can we use AI for surveillance?
Can I have more information of what is surveillance?
What do you mean? How can we use AI for surveillance?
Is it disease surveillance, for example?
I think so.
So yeah, so if it's disease surveillance, it's the same type of response that I responded to our colleague from Senegal. We can do monitoring of disease and be able to identify or predict outbreaks or patterns, seasonality, things like that. So these are applications in epidemiology or disease surveillance. And what we need is historical data of good quality, of course, where we will be having information on the disease at so I can't respond into details why, because depending on what you're trying to observe and what type of disease is this, you need experts like clinicians or epidemiologists that know the disease, that will be able to identify what type of data. People should work with data scientists, of course, to identify what type of data is needed to be monitored, collected, in order to be able to do surveillance and prevent outbreaks, peaks, etc.
Okay. So, what is the
We have another
intersection?
question.
Yeah, what is the intersection between statistical bioinformatics, AI, and data science? What additional skill set does someone with a master's in data science need to work as a bioinformatician?
Okay, so this is one of my favorite questions. Okay, so bioinformatics can be defined more or less as data scientists for biology. So as data science for biology. So the term data science is very recent, but the work of data science have been existing now for multiple decades. So bioinformatics is a data science applied to biology, which means that these are people that will be either developing tools, algorithm, statistical methods, and then performing analysis. Each type of analysis that you can think of for biology. So we have the aspect of developing tools. So these tools cannot be the very basic tools, or like not basic, but the popular tools that any data scientist will learn in college or during courses. Why? Because the biology has a very complex type of data that need to be analyzed. So bioinformatics is data science for biology, and it's a kind of high-level type of data science. As you first need to understand the biology, probably you will need to understand also chemistry and physics, depending on whether you're doing genomics or you're doing like structural bioinformatics, which is another subfield of bioinformatics. So you need to have this background of the type of biological data that you're analyzing. So you need to understand the biology, the chemistry, and the physics behind. Then you need to have a lot of skills related to coding, informatics, algorithmics, and data analysis. And then you become a bioinformatician. So that's more or less the comparison between bioinformatics and data science. So whether a data scientist is able to do bioinformatics, if the person is very elastic and able to learn new information, new concepts that are coming from biology, and this person never had courses or advanced courses in biology and related fields. This is what you need. You need to understand what is the biological question. Then you need to understand in what format your data comes. And then there is the informatician or the computer scientist that come into that. And then you bring your data science into that. And then you'll be doing bioinformatics somehow. Schematizing.
Okay. So another question. Are AlphaFold models based on AI reliable for molecular docking and molecular dynamic simulation for non-crystallized protein?
Okay, so AlphaFold is an AI model, basically, that have been learning over all the data that is out there on crystal structure or any type of experimental structures of proteins. So it have learned over experimental data of protein structures, and then it is able to predict the structure of novel molecules, to which we did not resolve the structure experimentally. So it's a prediction of this, the structure of the protein. That's basically what it does, AlphaFold. Now, if you would like to perform molecular docking or molecular dynamic simulation on these models, this is feasible, but you need to make sure that your model is very reliable. Whenever you're doing molecular docking or dynamic simulation on a model and not on an experimental data of your protein structure, you are adding up some errors in your system. So it depends to which extent you are, let's say, able to work with that type of errors in there. Depending on what you're doing, you can do molecular docking and molecular dynamic simulation, but you need to make sure that your model is good and to correct for any type of errors based on literature and other experimental data of similar proteins, if any.
Okay, thank you. So another one. Okay, don't forget to provide your comment on the link in the chat. And let's see. More question?
Good afternoon, Doc. Can you hear me?
Hello.
Yes, can you hear me, please?
Yes, yes.
All right, good afternoon. Thank you for the presentation. Unfortunately, I joined a little late, but so far so good. I've really enjoyed the presentation and the answers that Dr. Emma is giving. But my question is about bioinformatics and data science, because I'm the one who asked a question about the intersection between statistical bioinformatics and data science. Because I'm just getting started with a master's in data science, but I have the option of taking elective courses in bioinformatics. But when I look through the curriculum, it shows that I can take electives on analysis of protein expression, analysis of sequencing data. So I wanted to know from Dr. Emma, the kind of electives that I can focus on if I would like to maybe take up some roles in the future as a statistical bioinformatician.
So depending on what type of job or subfield of bioinformatics you're trying to work in the field in the future, it's very important to maybe if you can approach people or bioinformatician and learn about what they do. So bioinformatics can be split in, let's say, 3 major subfields. So we have the classical way where we use statistical bioinformatics to analyze sequence data, genomics data, etc., where we are trying to understand what is happening in the sequence of biological proteins, etc. So this is probably what any bioinformatician would be learning first. It comes with protein or sequence alignment, system motif identification, etc., etc. So that's the basic. It's not a subfield. Then we have bioinformatics that is focused on omics data. That's what all data that is issued from next generation sequencing and all type of new sequencing analysis. So these are high throughput data of sequences. And at this level, you need to be very skilled dealing with big data and analyzing data automatically. There is no analysis that can be done roughly or by analyzing subset of small analysis. Then we have the structural bioinformatics field. That's my field of expertise. And this is what is everything that is related to structures, 3D structures of biological systems, mainly proteins, but not only. And these are, so the AlphaFold is part of this field, subfield of bioinformatics. And it basically studies the structures of macromolecules in the 3D space. And for that, you need to have some chemistry and physics courses. So you can do this type of structural biology. It's rather chemistry and physics than biology courses that you need to know actually for that. And then what we have, the last one is what we call systems biology. And this is related to integrative approaches to analyzing protein-protein interactions or protein-genes interactions and connection between pathways into within biological systems. So these are the main big subfields of bioinformatics, and most of the time bioinformatician would be specialized on one of them and not necessarily working on the other one or two of them. So it is good to learn about these subfields and try to target what is your field of expertise and take courses that will help you really dive in there.
Thank you, Doctor. So we close the session, and can we get the presentation slide? There is someone. Can we get it?
Unfortunately, I can get part of the presentation slides, but not all of them. But yeah, I'll try to have like part of the slides if you share it if you'd like.
Okay, thank you, Doctor. Thank you, everyone. And I think that's all.
Thank you.
Well,
thank you,
everyone.
thank you.
Thank you for the invitation. It was a pleasure.
Bye, it's a pleasure.
Thank you, Dr. Emna. And just as a reminder, certificates will be issued to those who consistently attend this lecture series over the next 3 months. And we thank all the participants, and Dr. Emna, we cannot thank you enough for this amazing lecture. And we can connect with you. Yes, so we have her information on the screen. So please connect with her and follow her work.
Yes, please.
All right, so we'll see everyone at the next session, and we'll try to get more people. Today was